Today's topic is thin films. According to the syllabus, that's supposed to be yesterday's topic. But still, because of the snow day, we're exactly 1 day behind the syllabus. I want to start from a question. So what is happening to light when it travels from one medium into another one medium? So answers involve different variables: frequency, period, speed. So if you choose the answer, all parts are supposed to be correct, okay? Should have 2 more responses. 1. Okay. And then distribution. Not good. Well, it's a review question, so what we're supposed to remember that the frequency is a property of a source, so it doesn't change, it remains the same, as well as period. So the frequency changes, that's just plain wrong. Frequency stays the same, that is correct no matter what. It could be the situation like that, water, air, or air, water, doesn't matter, frequency doesn't change. What else changes? Of course, the speed of light changes. So speed changes, and speed, frequency, wavelength are related like that, so wavelength changes as well. That's the right question, answer. And now, I'm going to ask you this question. Let's just take a look at the apple. This is a mechanical model of a reflection of light when it bounces off the interface between the media. Here, we can assume there's a boundary, that's the medium number 1 and the medium number 2. The red row, light one, represents the medium with a lower index of refraction. And the pale one, the blue one, represents the medium with the higher index of refraction. What is happening to the pulse when it reflects? It changes its phase. It was up, now it's down. So this wave, after the reflection, has the phase difference of 180 degrees relative to the incident wave. So this kind of reflection always happens with the phase change. Now let's take a look at another case. This situation represents, well, say water-air case. The first medium has higher index of refraction, and what's happening now? Light is traveling towards the boundary, getting reflected, and after the reflection, that reflected wave doesn't have any phase difference at all. So for the light, when it's bouncing off the interface, we may have two situations. Yeah? Number one, no phase change like this, when the index of refraction of the first medium is higher than the second. And number two, with the phase change. And this phenomenon now, in addition to conditions for maxima and minima, explains a lot of different experiments. Well, let's see if I can make it work. This is my camera. The first experiment here, I have just a regular standard soap solution. And here, well, I want to make a soap film. Actually, let's show that's what it is. Soap solution, soap film. Probably you cannot see it from afar, but it's there. Everybody done, you know, bubbles. And now, this is a really cheap camera, but if you look closely, you can see horizontal lines. An eye actually is much more sensitive. Could you please take a look at it? So you would see what I see. What do you see? And what's happening to those lines? Oops. They popped. Yeah. They actually move down. Well, first of all, they have some colors. Green, red, and they move down. And at some point, the part on the top becomes dark and large, and eventually, you can actually, if you look closely, you can see that at the bottom, those lines much thinner than on the top, wider on the top, and well, that's what is happening. That's what we call a thin film, and those lines which you see are a result of the interference. So this is a phenomenon which we call thin film interference. There are different, actually practical applications of thin film interference. If you have a good for the camera, well, nowadays even that for the camera, always has a lens with some thin film coating on top of it. Why? Well, because of the interference. If you use that coating, you actually can amplify some light of specific wavelength traveling through. Here, let's see. Okay, that's what you see now. That's what you see now. You see? When I add this glass, the picture becomes kind of bluish. And what does it mean? It means that, well, blue light is getting through, and other colors actually not. That's why it's bluish. So with a device like that, we can amplify, well, blue light or light of other wavelengths traveling through this glass. Why? How can we? How do we do that? Well, we place a thin film of special material with a specific value of index of refraction. In that case, the blue light actually not getting reflected. But if not getting reflected, that means it's all getting through. You could look through this glass and you see it actually makes everything kind of bluish. And there's one more phenomenon, we call it Newton's rings. Basically here I have two lenses placed together, and where they touch each other, you can see some colored, well, ideally that would be colored rings, but shapes actually kind of curved. Let's see if I could make you see it. I can see it. An eye is much more sensitive. So if you look, well, the lens doesn't catch it. All right. But if you look through the lens, you can see colored shapes around it. And the goal for today is to explain all those phenomena. Well, the simulation this simulation helps to understand how the thin film interference is happening. What we have here is three media, number 1, number 2, number 3. So 3 indices of refraction are involved, 2 interfaces, 2 boundaries. And what is happening depends on the relationship between the index of refraction of the media number 1 and number 2, and then between the index of the medium number 2 and number 3. We know that in a case where this index of refraction is less than this index of refraction, we discussed it a minute ago, in that case, that after the reflection, light changes its phase. So let's take a look at one specific situation. So this is the relationship between the index number 1 and index number 2. So we call it air, water situation, water. And here, on the bottom, the index of refraction number 2 is greater than the index of refraction number 1. We call it water-air situation. In actual experiment, that could be actually, well, air, well, say water, and say some kind of, well, air again, well, or some kind of plastic or glass with index of refraction less than index of refraction of the water. So that's the incident rate. Of course, when it reaches the boundary, a part of this light getting through and a part of this light getting reflected. So here, what we see is the phase change. This is happening because the index of refraction number 1 is less than the index of refraction number 2. Now, the incident ray is keeping approaching the next interface. And now, another reflected ray is going up. However, now, do we see any phase change? No, we don't. Because for this situation, the index of refraction of the second medium, for this situation, that's medium number 1, that's medium number 2. The index of refraction of the second medium is lower. It's less than index of refraction of the first medium. going to happen next? Look at this region. So you have two waves, they move like that. What is going to be happening here? And we have only two possible options. Number one, constructive interference. Number two, destructive interference. So these two waves either amplify each other, which means we have a stronger reflection of light, or these two waves actually cancel each other out, which means there is no reflection and light completely getting through. So here, if you look at this situation, what do you think is happening? Constructive interference or destructive interference? Please make your mind, because I'm going to erase this just in case. So 1 or 2. And now, please enter your answer. Okay, 25. Exactly. Thank you very much. You made me happier. After class. So, since two waves are out of phase, they cancel each other out. So, this example shows when light doesn't get reflected back. So, if there is no reflection, it actually travels through this optical system completely. Well, however, there are several conditions which must be fulfilled. Number one, that was an important condition. Number two, that was the important condition. And number three, if you look closely, here, inside the second medium, which is the thin film, we can fit exactly one wavelength of light. So, exactly one wavelength. What do you think would happen if we could fit exactly 2 or 3 or 4 lambda? Would it change the result? No. So, another important condition is how many, well, lambda or half of lambda we could fit the thickness of the thin film. Now we just have to mathematically describe this phenomenon. You actually can find a very similar applet online. If you go to Essential Physics website, Professor Davis website, you can play with this applet or many other applets I've been using before. So that might give you a better feeling on what's happening. So we just answered here for this particular case, because waves are out of phase, they cancel each other out. To analyze all possible situations, we can use so-called 5-step method. You have a copy of this page. So basically, what we got, and you have actually a copy of these 2 pages. These 2 pages describe all possible situations, all possible combinations. We have index number 1, index number 3, number 2, number 3, and there are so many combinations, which is greater, which is smaller, and light might be traveling in all directions. So these pictures show you all possible combinations. If you want, you can memorize all those combinations. But it's much easier to use a straightforward 5-step approach? Well, where is it here? We apply that approach to solve this particular problem. So this is the problem. Light is traveling like this. Air, oil on the surface of water. Well, this thickness is millimeters, micrometers, so that's fairly thin. And there's an observer which is looking at that film. And if you're seeing puddles with oil, you can see actually some kind of colored shapes. What we know is the wavelength, all indices of refraction. Now, for all problems like that, we make an assumption that light is practically perpendicular to the surface. So this is kind of the actual situation, but what we think of this, it happens like that. And the person is here. The light goes down, reflection, and here they interfere. And we can observe either cancellation or amplification of light. So we always can neglect this distance, and we always can neglect any of the angles. This is a short solution now. Let's see how we should apply the method. So first of all, again, you have to draw a picture. You need to see what is happening. So I would recommend just do whatever I do. Air. Then oil. Fine. And water. So light at first reaches the interface between air and water. Of course, we know for sure a part of this light getting through. The question is, here, should we observe any phase change or not? And the rule is, if we observe, well, let me say what we're actually looking for. That the result depends on path-length difference, as we know, right? So when light is traveling down, and then when light is traveling up, and this is how thick the film is. So the path-length difference between this ray and this ray is supposed to be equal this. One thickness down, one thickness up. However, depending on the situation happening during the reflections, we should either say there is no phase difference. If there is no phase difference, that means we do not have to change this path length difference. In a case when 180 degrees phase difference happens, in that case we say we should add an additional half of a wavelength to path length difference. And this is what we call the effective path length difference. That's what our ultimate goal is, to calculate this. So we know for sure this term is supposed to be a part of this difference. But what about this part? And what about the reflection on the bottom? We also should, or maybe not, add an additional half of a wavelength because of that reflection. So, first thing to think about is, do we need to add or not an additional half of a wavelength related to the possible phase change during the reflection? So, here, air, oil. What's supposed to be an additional, if any, path length difference be equal to for the ray reflected on the top of the film? That's the top of the film. That's the bottom of the film. So this term represents the possible additional path length difference which is happening on the top of the film. These are your possible answers. So what do you think? Okay, we should add that additional term, so most of you are correct, because this boundary is air-water kind of boundary, and 1 equals 1 and 2 equals 1.3. So, and 1 is less than 1.3. It's like light roll, heavy roll. That reflection involves 180 degrees phase change, which results in an additional shift in path length difference. All right. Well, on the bottom, 1.5, 1.3. Higher, lower. In this situation, we shouldn't add any additional path length difference. I'm going to ask you this question. So now, since we know both terms, we can go into the next step and we can calculate the effective additional path length difference. It's going to be the bottom one, which is 0, the top one, which is a half of a wavelength. Well, we need the actual value of that. Okay. Now we need to remember, that's very important, because 50 chance, well, you may forget it. It all is happening inside the film, inside the medium. So that's supposed to be the wavelength in the medium, not in the vacuum. So the wavelength in the medium is, remember, equal to the wavelength of the light in the vacuum divided by the index of refraction. We have 3 indices of refraction in this problem. So which index of refraction do we need to use here? It's all happening in the film. So it has to be the index of refraction of the film, which is, in our case, 1, 2, 3, the medium number 2. So don't forget that. Now, so now, the actual effective path length difference is going to be equal to T plus this one. And we supposed to set it to either condition for the constructive interference or the condition for destructive interference. It depends on the problem. We have to read the problem. What does our problem tell us? So, when looking straight down at the film, the reflected light is orange with a wavelength of 600 nanometers. Well, first of all, this is the wavelength in vacuum, 600 nanometers, 10 to the 9 meters. So the wavelength in the film is supposed to be, well, it's L2 equal this number divided by 1.5. That's the wavelength we have to use. Now, if we see this light, it means it is actually getting reflected. So we're looking down and we see orange. So that means those two waves do not destruct each other. They amplify each other. That means a constructive interference is happening. If we would be told we do not see reflected light of this color, that would mean what? They cancel out each other. So we write again. In our problems, we have to set it up to what? This. Well, M, some, well, in general, integer, 1, 2, 3, etc., etc. And now we can solve this equation for what we're looking for. In this problem, we are looking for how thick is the film. That's T. Well, that's supposed to be equal to that's the thickness of the film. So it cannot be negative, never. Right? Well, smallest number for the thickness is 0, technically, but it can't be negative. So that tells us which value of M we should choose for the smallest possible value of T. We can just try 0. If we try 0, 0 times lambda is 0, 0 minus lambda is a negative number. 0 doesn't work, so we go to the next number. We can try 1. So for the 1, it's going to be 1 times lambda. Lambda minus a half of lambda, the result is lambda over 2, or a quarter of a wavelength. Of course, that's not the only possible thickness which gives you the same kind of reflection. You can get M equals 2 or M equals 3. So there is a set of possible thicknesses which would give you exactly the same reflection, amplification of the orange light reflected off this film. And again, don't forget, this is actually in the medium, in the film. So if you want to calculate the actual value, that's going to be the wavelength in the vacuum divided by the index of refraction of the film divided by 4, or 600 nanometers divided by, well, it's 4 and it's 1.5. Let me write it again. So it's going to be 600 nanometers divided by 4 and divided by index of refraction of the film. Not the air, not the water or glass, film. And of course you can calculate this number Any questions? Because that's how the method works. We just had it covered here. It's just a clear representation, written representation of what's happening. That's the first term related to the top interface. That's the second term related to the bottom interface. There is no big difference. Now the effective pattern difference is always thickness down, thickness up, plus, well, wherever we get. And we're supposed to set it to, in this situation, constructive interference condition. And if we solve it, we get a set of possible thicknesses. And it's a so-called a quarter of wavelength film. If you want to amplify a reflected light of specific color, you can coat it with this particular film. Well, and now you can solve any problem. This problem is related to this kind of device or related to this situation. Well, here what we have is a film of air between two pieces of glass. And if you look at it from the side, you actually can see, again, colored lines. Why are they there? How does it happen? Well, in general, this kind of air wedge is just an example of a thin film. However, the thickness of this film varies. So we just had calculated for specific thickness, orange light getting amplified, which means for a different thickness, blue or green or yellow light will be amplified after the reflection. So depending on the thickness, if you look down, at some point you can see red, at some point you can see green, and that's how we see those colors. So in this example, again, you can apply 5-step method. Glass, air. This reflected ray doesn't experience any phase change. Heavier, lighter. So the incident ray splits, reflects, and refracts. Again, we neglect the effect of refraction. We think all rays are parallel to each other. Now another reflection is happening here. Well, again, air, glass. So at the bottom interface, the phase change is happening, which means we're supposed to introduce an additional term into the effective path length difference. So the effective path length difference now supposed to be equal to thickness down, thickness up, plus, well, 0 minus a half of a wavelength, 2G plus this. So let's say, again, we want to amplify the orange lights. For the orange, the wavelength in vacuum equals 600 times 10 to the negative 9 meters, 600 nanometers. So first of all, now this is air. The film is air. And the wavelength in the air is equal to the wavelength in the vacuum, because the index of refraction of air is 1. And again, if we want to see the orange, we have to set this condition to maximum. That's it. Another question would be, okay, if we don't want to see the orange, which means a person below on another side of this field wants to see it. So there is no reflection back. That means light travels through. Because that's only the options. It's either getting reflected or getting through. So no reflection means now these two rays supposed to cancel each other out. And in that situation, what we do? It's still the same expression for effective pattern difference. But now we have to set it to a condition for diffract interference. And we have to solve it for the thickness. And let's do that. So 2t plus a half of wavelength supposed to equal to 2m minus 1 times a half of wavelength. If we want this particular light at that particular place travel through. If we don't want this particular light at that particular place getting reflected back. Well, let's work it out. 2m lambda over 2 minus lambda over 2. And what we want to solve for the thickness. T equals m cancels, so m lambda minus over 2. It's just pure math. And if I take this term and I bring it over here, I get negative lambda over 2 minus lambda over 2. And I have to divide everything by 2 in the end. So now m would be, well, any integer. However, there's again one condition. The thickness cannot be negative. It cannot be negative. It could be 0, or it's some non-zero number. So if m equals 0, what does it tell us? It gives a negative thickness. It doesn't work. If m equals 1, what does it give us? It gives us 0. When is thickness 0? Of where? Here, in this region, very close to the edge of this wedge. So here, this end of the wedge has to be dark if you look from above, because there is no reflection happening over there. And that's what we saw here. Now, over time, well, when the soap film actually, because of the gravity, is getting pulled down, what you're getting there is a soap film like that. It's the same wedge, it's just vertical. And here, the thickness is practically 0, so light doesn't get reflected. And that's why when we look at this like this, in this region we see nothing, black. Well, these are much better pictures of that experiment. And here on the top, you see there's no colors at all, and it pops eventually. It's getting thicker and thicker at the bottom and thinner at the top. So this region, black region, getting larger and larger. And the 5-step method gives you the effective pattern difference. The difference between the air wedge and oil or film wedge is that now what you have is air outside and film inside, right? So what a case like that, what you get. Let's say you are here and you're looking at light which is getting reflected. So that's going to be your medium number 1, that's going to be your medium number 2, that's going to be your medium number 3. The first reflection, air film. Of course, here the phase change happens. First step, the effective path length difference at the top is supposed to be a half of a wavelength. Again, don't forget, that's a half of a wavelength in the film. However, here there is no phase change because this index of refraction is 1 point something, this index of refraction is just 1. So this is going to be our effective path length difference. And then you can set it up to a particular wavelength. If you want to see green, you set it up to constructive interference. If you don't want to see red, you set it up to destructive interference. And yeah, the thickness here, when it approaches to 0, results in no light gated reflected at all. Well, and that lens I passed around, Newton rings. Again, exactly the same situation. You place a lens, and here, between this glass and between this lens, we have the air wedge. Well, it could be air wedge, but we can take this apparatus and we can put it in water. So, in the most general situation, and you should have actually this page so you could go to this applet and see how it works. So, in general, what can you have? Well, that could be glass. That could be, let's say, plastic. Or that could be water. So a light goes like this. First reflection, second reflection, and here they interfere. How? Constructive or destructive, depending on what you want. If you look from above, and why we don't see any light here? Why is it a black ring? Because completely destructive interference had happened. Light is not getting reflected. Here, back is getting through. And here, the red ring we see because not constructive interference happening, light getting reflected. That depends on thickness, and the thickness depends on the radius, and you can actually calculate the location and the radius of each ring, black or red or green or wherever. Any questions? Well, thank you for coming. On Monday we're going to talk about special relativity.